Hello, welcome back. This is chapter 8.3, and in this lecture we're going to have a look at oxidation reactions of alkenes and the addition oxidation reactions of alkynes. So let's have a look at the video breakdown. There are going to be 3 videos for this lecture. The first one covers the oxidation of alkenes. The second one looks at oxidative cleavage reactions of alkenes, and the third looks at addition reactions to alkynes and then the oxidative cleavage of alkynes. The oxidation of alkanes as a concept involves increasing the number of bonds to carbon to electronegative atoms, and in particular oxygen. An alkane can be oxidized to an alcohol, that's 1 bond to oxygen, which next can be oxidized to an aldehyde, that's 2 bonds to oxygen. After this, the aldehyde can be oxidized to a carboxylic acid, which is 3 bonds to oxygen. Finally, that carboxylic acid can be oxidized to carbon dioxide, which has 4 bonds to oxygen. Please note that the O in the square parentheses represents the oxidizing agent. Now there is also a cyclic example on this page, and the carbon highlighted here is a cyclic ether, and this has 1 bond to oxygen. So this is less oxidized than the next cyclic ether and alcohol, which now has 2 bonds to that same carbon. And finally, the last example shows a cyclic ester known as a lactone, and this is the most oxidized of these carbon atoms because it contains 3 bonds to the oxygen atoms. Make sure that you annotate in your notes which is the least and the most oxidized examples on this slide. Pause the video while you do this and move on when you are ready. There is a 5-second timer between this slide and the next one. There will be 2 key reactions that we look at in this lecture. They include cis-dihydroxylation, which provides a synthetic route to cis-dihydroxylated diols. The second reaction is known as an oxidative cleavage, and whilst only one type of product is shown here, these are aldehydes, it is possible to synthesize ketones and carboxylic acids by the cleavage and oxidation of an alkene substrate. We'll consider what can happen to alkyne substrates by this second reaction route in a later video. Let's have a look at the diol formation from an alkene first. There are 2 possible methods by which to effect a stereospecific syn addition. However, there is a temperature dependence for the first route because otherwise oxidative cleavage can occur. This we'll see on a later slide in a later video. When an alkene substrate, for example cyclohexene, is used and a 2-step reaction sequence applied, then a cis-1,2 cyclohexane diol results. In the first reaction, potassium permanganate is used as the oxidizing agent in the first step, and this is followed by an alkaline workup in the second step. Note that the reaction has to be kept cold, otherwise unwanted oxidative cleavage will result. The mechanism for any of the oxidation processes are beyond the remit of this course. In the second reaction, the same result is achieved, but osmium tetroxide is used as the oxidizing agent in the first step, and this is followed by a second step which uses an aqueous sodium bisulfite workup. Whichever reaction you use, enantiomers of these are possible. That means that you will end up with a racemic mixture. However, don't forget about the possibility of meso compounds. These reactions would in fact produce meso compounds because of an internal mirror plane that is present in both of these products. Please remember that acyclic cis-Z alkenes with R groups that are the same on either side of the double bonds will lead to a meso compound, and this is irrespective of whether you use cold potassium permanganate or the osmium tetroxide as the oxidizing reagent. Also note that the attack of either reagent is a syn addition to the alkene, which means that this can be achieved from above or below the plane of that alkene. An acyclic trans or E-alkene with the same R groups either side of the double bond leads to a racemate. Though both diols are possible, the attack, like before, comes from either above, which is the case of this alkene, or from below, which would be responsible for the other enantiomer.
This concludes part A.
In this video, we're going to look at the versatility of the oxidative cleavage reaction. If you remember, in the last video we discussed the temperature dependence when using potassium permanganate to affect cis dihydroxylation of an alkene substrate, and that reaction is shown at the top here. Now, to pick up on that thread of discussion, then if heat is used under alkaline conditions, the oxidative cleavage of either a cis or trans alkene, in this case we happen to have a symmetrical acyclic alkene, results in two carboxylate groups, e.g. acetate ions. Had we used an alkene which was not symmetrical but contained an internal alkene, this would result in two carboxylate residues that contain the same number of carbons as the original alkene substrate. Acetate anions can then be converted into the corresponding carboxylic acid, in this case acetic acid, via an acid workup. What this does is it protonates the carboxylate group, and we see the two acetic acid molecules as the result of that reaction. Now, in the last reaction, if the alkene is placed in a terminal position or it has two hydrogen atoms at the end, then a ketone is produced. The pink portion of the alkyl chain shows where this ketone product comes from, but the carbon in green would be oxidized first to a dicarboxylic acid, but then in situ it would be oxidized all the way up to carbon dioxide and water, and this provides a completely balanced equation. So this is an overview. Let's break this down on the next slide. Numbering substrates is your friend, and you are encouraged to do this on this course to a substrate in all cases. Now, the scissors represent where the oxidative cleavage is going to take place, and it's worthwhile noting that the potassium permanganate will never yield an aldehyde as a product. The only products possible via this two-step reaction sequence are either a ketone, a carboxylic acid, or carbon dioxide. Now, in this example, all three functional groups are possible. The aldehydes that are produced in situ will always be oxidized up to a carboxylic acid. So this is why you never isolate them when using potassium permanganate, and certainly not when there's heat involved. See if you can figure out what the possible products are for this reaction. There are three possible products. Pause the video and resume when you have an answer. The first product happens to be a carboxylic acid, as an O atom is added to carbon 5. The second product contains a carboxylic acid at the fore end, as the O atom was added, but at the other end only a ketone is produced. Adding an O atom here would yield a carbon atom that has violated its octet. Finally, you see the dicarboxylic acid as the product for carbon 1, but what actually happens is that the dicarboxylic acid is oxidized in situ to a molecule of carbon dioxide and water. A natural question that you may be wondering after seeing this slide is, well, how do I get an aldehyde then using oxidative cleavage? Let's take a look at that now. To reiterate, there is no need to learn the mechanism for any of the oxidative processes on this course. However, you will be expected to know the possible results of this milder two-step oxidative cleavage reaction scheme. Here the use of ozone, and this happens at -78 degrees Celsius in a dichloromethane solvent, causes the oxidative cleavage to occur. The second step uses zinc and water or acetic acid. to yield the aldehyde and ketone products we see here. As seen on this slide, the hydrogen on the right hand portion of the alkene becomes the aldehyde, whereas the disubstituted chain on the left side of the alkene is what is responsible for the ketone.
This concludes part B.
And in this video we're going to discuss the electrophilic addition reactions to alkyne substrates. Now, for the halogenation of alkynes, the addition of a single equivalent of a halogen, i.e. bromine or chlorine, yields an alkene with E or trans stereochemistry. With a second equivalent of a halogen that is added, this would lead to the synthesis of a tetrasubstituted haloalkane. Now let's have a look at the hydrohalogenation reactions for alkynes. The reaction of a terminal alkyne with, say, hydrogen bromide proceeds with the same regiochemistry as for an alkene, which is by a Markovnikov addition. If a second equivalent is added, then this provides synthetic access to geminal dihalide products. The second reaction shows anti-Markovnikov products are also possible with a terminal alkyne. So a single addition of hydrogen bromide in the presence of an organic peroxide or hydrogen peroxide would yield an E or a Z alkene, which places the halogen atom at the terminus of the molecule. Let's now look at the hydration reactions of alkynes. The hydration reaction of a terminal alkyne using hydroboration oxidation yields a product known as an enol, and for reasons beyond the remit of this course, these rearrange to give a more stable product, that is, the more familiar aldehyde. Whereas mercuration demercuration provides access to methyl ketones via a different stabilization pathway. Both pathways are concepts that you will learn about on the OChem 2 course. The next concept that we're going to discuss is the oxidative cleavage of alkyne substrates. Internal alkynes provide the same outcome whether a milder or harsher oxidative cleavage condition is used. These both provide access to carboxylic acids only.
This concludes part C.